Titans NeuralMemory Engineering Practice. From Google's 2025 research paper to a working engineering implementation. HSOFormerTitans integration with OpenClaw Bootstrap pipeline. Open source release, May 2026. Titans is a Google research architecture from 2025, featuring a 3-level memory system. Persistent memory stores trainable parameter matrices for cross-session knowledge. Contextual memory uses surprise-driven dynamic updates. When the gradient exceeds a threshold, the memory writes. Ephemeral memory handles traditional transformer attention. The key innovation is making trainable memory a first-class architectural citizen, supporting over 2 million token context windows. Since Google has not open-sourced their implementation, we built our own engineering version using the community LucidRains library, and integrated it with the HSOFormer architecture for a complete memory plasticity system. The HSOFormerTitans architecture follows a clear pipeline. Input goes through an embedding layer, then neural memory for memory-augmented processing, then 2 transformer encoder layers, then output projection. The critical innovation is state passing. Memory weights persist and evolve across sessions, not just within a single forward pass. Key components include neural memory for chunk granularity memory queries, adaptive step size for per-input update control, forget gates for exponential decay of outdated information, and momentum for state accumulation across multiple iterations. The architecture alignment between HSOFormer and Titans is precise. Hebbian plasticity maps to neural memory gradient descent updates. Time decay maps to forget gates with decay factors. Synaptic consolidation maps to momentum-based state accumulation. The meta-controller maps to learned adaptive step rates. Verification results are convincing. In Experiment 1, neural memory plasticity was confirmed. Without state passing, the output difference was 0, deterministic behavior from scratch. With state passing, the maximum difference reached 3.35, proving that memory weights were updated. After 5 state accumulations, outputs continuously diverged, confirming the plasticity mechanism works reliably. Experiment 2 tested training convergence on a hidden sequence pattern memorization task, learning the first 8 digits of pi. Initial loss was 5.37, final loss 0.21. Pattern accuracy reached 100% after training. Experiment 3 verified the integration. OpenClaw Bootstrap loads Titans memory at every session startup through agents.md order 3.95. The automated pipeline has 4 scripts running daily, managing an 18 MB state file for cross-session persistence. The entire system passed 3 rounds of interactive verification between OpenClaw, Copilot CLI, and the project lead. OpenClaw integration is deep. The Bootstrap chain loads Titans memory context at every session startup, from sol.md through user.md, daily memory files, skills, all the way to Titans memory brief at step 3.95. The automated memory pipeline runs daily. The consolidator extracts high salience entries from session logs. The brief generator compresses to the 8 most relevant entries with importance and confidence scores, and the validator checks for prompt injection safety. The tiered architecture has 3 levels. Tier 0, already in production, includes the memory pipeline and prompt injection into every session. Tier 1, verified through experiments, includes the HSOFormerTitans neural memory module. Tier 2, under development, targets 100 billion plus parameter distributed scaling. 5 key engineering lessons. First, a paper without open source code does not mean it cannot be implemented. Second, third-party community libraries can fill the gap quickly. LucidRains released Titans PyTorch shortly after the paper. Third, architecture grafting, integrating a new module into an existing architecture, is much faster than building from scratch. Fourth, state tracking is the absolute key to memory plasticity. Without passing state, there is no cross-session memory. Fifth, integration depth matters more than feature breadth. A deeply integrated simple memory system beats a complex system that is bolted on. Recommendations: start with proven libraries, not paper reimplementation. Build the memory pipeline before the model architecture. Verify plasticity before investing in training. Use Bootstrap integration for maximum impact. How to use this repository. Quick start: install the Titans PyTorch library, then run the HSOFormerTitans demo script. Run the test suite to verify neural memory plasticity and training convergence. Integrate into your own architecture with just 3 lines of Python code. Import neural memory, initialize with dimension and chunk size parameters, then call the memory function with input and optional prior state for cross-session persistence. Full documentation and examples are on GitHub. Thank you. This project is open source. May 2026. By Anne.